right. Can you hear me?
Yes.
Yes.
Good. So how are you doing?
Pretty good.
Good. So let's start then. There are two things I want to say. First, last lecture on Friday was canceled completely unexpectedly from me. The same was probably for you. So I had to think of something, and then I received that emails, and I spent some time checking that it's not a fake email from some fronters or whatever, and then I sent the announcement. Well, I'm very sorry about it, but well, there's nothing I can do. That's the first thing, and the second, last lecture which we had on last Wednesday. After the lecture, I checked the chat room, right, which you had, and some people complained about the quality of sound. Look, I don't know what to do about it, right? Internet, I don't govern internet, unfortunately. Otherwise, it would be perfect. But so that's the reason I come to my office to give these lectures. Right? I could have done it from home, but I know that my internet connection at home, although it's not that bad, but it sometimes is interrupted. So I come to my office, so I have the best which is available to me. So chances are, if you have bad connection, but then it means it's problem on your end. It's not necessarily so, but it's the most probable cause of it. So try to find some place where the connection is better. You can come on campus if you want, or whatever. It's I don't know where you are, right? Not all of you can come to a campus, but nevertheless, try to figure out what place has the best connection and so forth. That's the only thing which we can do. Otherwise, if the interruption becomes very bad, just say so. So I'll repeat myself if you haven't heard anything, or so let's work around it. There is nothing more we can do. All right, so I'm going to talk about the homework first, and then the material of the lecture. And for the homework, I want to go through it quickly because it's the material is quite a lot. In fact, I tried to squeeze in one lecture what I teach about 1 month in analytic mechanics class I teach in the fall. But again, I'll talk about it. So homework. The first problem is to find whether the force is conservative force or not. And majority of you get it right. It's just a simple calculation, right? You just take the derivatives and see if they match or not. You can compute the curl of that vector field if you want. Although for 2 dimensions that's overkill. But in more dimensions, that's well, in 3 dimensions you can do that. Or in 4 dimensions, curl cannot be defined. And so there are different ways, but the cross derivatives will always work for any dimensionality of the space. So in some sense that's easier to do. And the only problem which pretty much everyone had is you miss the last constant after the last integration when you find the function u, which gives that potential function which gives those forces, the force A. Right, there is a after the last integration, there is still some unknown number, arbitrary number, which hangs around, right? And it must be defined by choosing one of the points to have, say, some particular potential, for example, 0, like a ground, like on electrical circuit. And but it's better if you haven't done that. It's better to keep it. Right, so that you don't miss defining it somehow, or you don't miss a chance to define in such a way that the rest of the calculations are simpler, and so forth. So it's not a big problem, of course. After all, the potential which you gave indeed gives that force. There is no problem with that. It's just not the most general form of that potential, right? And so I took 1 point off. For those who didn't define that constant C. as an arbitrary constant. Just to attract your attention, right? Otherwise, if I give you full points for that, you will never look what you've done, even if I write any comments on it. So I'll skip the solution. I mean, it's it's just simple taking derivatives, nothing else. Now, the second problem was the idea was to derive this famous formula which everyone knows, unfortunately, because the students tend to stick it anywhere which it doesn't belong. Right? That formula is only correct when you have constant acceleration and never else. And in typical problems, the acceleration is never constant. Right? It's very, very artificial example when the acceleration is constant. So for those artificial examples, that formula can be used, but otherwise it's completely pointless and gives the wrong answers all the time. Please don't use it for any problem. But in this particular case, you are asked to derive it starting from energy conservation law and then going to integral representation and so forth. So you start with you're supposed to start with the potential energy, and the potential energy. Let me get, no, it's 8 here, right? Not 8. So the potential energy was minus m a x, right? So the total energy then is given by kinetic energy plus potential energy. And now what you're supposed to do is to derive that, to write here the following way. That E equals m over 2 dx over dt squared minus m a x, right? Then you just extract the dx over dt from here. And what you find is that this is dx over dt equals 2 over m square root plus minus, right? And then you have E plus m a x square root. It's exactly the same what I've done in the lecture. And then from here, you see that dt equals plus minus m over 2 square root dx over the square root e plus m a x squared. Right? And then what you find is that you have this solution. Right?
Yeah.
So this is the integral representation for it, but then this is very well defined integral, right? It's just a square root. You just take this integral, right? But maybe before you do that, you need to find out what are the initial conditions. That letter E here. You have initial conditions here, right? X naught and V naught. So you can compute that energy at the first moment of time. At the first moment of time, energy equals m v naught squared over 2 plus m a x naught. Right? So this is your given number. It will not change during motion. So you already know this number. If you give initial conditions, you're supposed to be given initial conditions. Or if you need to figure them out, then you just stick it here and it's just a number. So when you take in this integral, the only variable here is this one. And this is the integral of a square root. Right, 1 over square root. So the result is, of course, the square root. So it's plus minus m over 2 square root. And then you have, what do you have? E plus m a x square root. And now when I take in derivative of it, I get 1/2. So it will be plus minus 2. And I will have ma extra ma, so it's ma here. Right? And it must be taken between two boundary values, x naught and x of t. Right?
Professor, could you explain how you got the bounds for the integral x naught and x at t.
When
Yeah.
t equals 0, right? This integral is
Uh-huh.
supposed to be 0. Right? So this is exactly this function which you're supposed to find. That's the position of the particle at point t.
Okay.
Right? So at the initial point, that position is x naught. Right? Initial
Yeah.
point of t equals 0. So this
Mhm.
integral when x of t equals x naught must be equal to 0.
Oh.
Right?
Okay.
So that's why x naught is here, because then two boundaries coincide and you definitely get 0. Right? That's it. That's x naught, and this is the position which you need to find. So it appears here, right? So now you take that this equals to plus minus 2m over 2 1 over ma, right? And then you have here e, which you know, right, from initial conditions, plus ma x of t square root minus e plus ma x naught, right? Something's wrong here. Sorry. It's minus. Right. No one tells me. Come on, guys. Minus here, right? Because it's minus here. Square root. Right? That's your integral. That's all, right? All you need to do now is to do some algebra and extract this x of t, and and substitute instead of e, substitute this expression. Right? It's just simple algebra. You basically what you do, you give it, you take the square root, move it over here, square both right and hand side, and that's it. You extract it x of t. What you will get out of this algebra is the following expression: that x of t equals x naught plus minus b naught t plus a t squared over 2. It will happen. I mean, if you solve this equation, right? This is t, this is the equation, right? And this one. That's an equation which you solve, and you will find x as function of t. You solve this with respect to x of t, right? Is it clear?
Yeah.
Yeah.
So now, the only problem then which is left is this one, plus or minus. You see that it's almost the same expression as this one, except this plus minus. Again, it will appear because of that plus minus. So when you move in this part on the other side, it will carry plus minus, then you square it, and the cross term will still have plus or minus there, and so forth. So it will appear right here. And the reason for that plus or minus appearing here is the following. You see that velocity, initial velocity, in all of this calculation appears only here. Right? In the energy, in the value of energy. There is nowhere else there is V naught. Right?
Yeah.
But then you lose the sign of V naught because you square it. Right? Square of negative number, square of the same positive number is the same. Right? So you're losing the idea of what is the direction of V naught. And it always will happen in this kind of calculations because V naught is a vector and E is a scalar. E, energy, does not have direction. Energy is a scalar, right? And velocity is a vector. So you can, every time you find scalar out of vector, you will lose some information. You will lose the information of the direction of the vector. Because there is nothing to contain this information in them.
Unless you had like more initial conditions to back it up to determine the sign.
No. You cannot have more initial conditions. Right? Simply because you solve in second order differential equation. You must have only 2 initial conditions. If you have more than 2 initial conditions, your equations in general will not have a solution. Right? Second order differential equation, 2 initial conditions. That's all. It's very simple count. Right? So you were given initial initial conditions and correct number of initial conditions, but when you use it, you're losing some of the information on the initial condition, plus or minus, right? So you need to restore it here. And to restore it, it's simple. When the time is very small, you can neglect this term because it's time squared, right? When you take small number and you square it, you get smaller number, which is even smaller. And then what you have is just x naught plus or minus v naught t, right? So if you v naught, you can, and you should consider v naught to be positive towards the increasing of coordinates, right? So it means that it's plus, it must be plus sign. So you restore the plus sign from the simple consideration. So the idea was that to get this formula, which you know already, right? So it's always a good thing if you learn some new technique, right? Presumably more general technique, to use it first on something which you already know. That's how you check that you first of all understand the technique well, and second that it actually works, right? What if you made a mistake with deriving it? So it should be a general situation. Every time you learn new technique, you should come back and solve like old problems with new technique, so you know how things work out.
Wait, so how did we restore the positive sign?
Again, you lost it, right?
Yeah, because of the square.
Right, because of the square. So now you need to restore it somehow. Well, we're not positive when x is increasing, right?
Yeah.
So for very small times you can neglect this term, right? And you see that for very, very small times, x should be increasing if you notice positive. But
yes.
that's the only plus sign. The only plus sign will take care of it. Minus means that x is decreasing, right?
Yeah.
So that's it. Then it's plus sign. Right? So and again, this is in this technique, this particular technique, it is a general problem that you have to restore that sign because of that plus minus and ambiguity here, right? When I take in square root, I have to keep plus and minus. That ambiguity must be resolved somehow because the answer must be unambiguous. And well, that's a typical situation when it should be resolved like that. All right. But by the way, this is not a trivial thing. It's in quantum mechanics, this plus and minus sign are both working and both make sense. It's just the limitation of classical mechanics, which tells you that you need to pick one from something else, something which remembers the direction of the initial velocity. Right? That makes sense?
Yeah.
Yes. Yeah.
All right. So that was I tried to write it as explicitly in the problem as I could. Just write the integral representation, blah blah blah, all of this. And unfortunately, and don't take me wrong. The way you derived it from the energy conservation law is of course correct. There is nothing wrong with that. That's why I gave majority of the points for that. But it's just not what the problem was asking. As usual, and that should be understood as in general. Every solution, every problem, well, may have many solutions, different ways to solve it. They will all, if they all done correctly, they will all give the same answer. That's the beauty of math. Right? It allows you to choose the way to solve a problem the way you want to solve, whatever is easier for you. Right? And math is constructed in such a way that everything is done correctly, then the answer will be the same. And that's the power of it. And well, there's no unique solutions of the problem. So if you have your own solution, it may be even more interesting than somebody else's solution. Right? Okay, so next problem. You were given some potentials. So the first potential were kx to the fourth, and you were asked how its period of the oscillations in this potential depends on the total energy. So if you draw that diagram, which you should have done, because it's always good to have a picture. So this is potential, and so this is x, this is u, and so if you have a given energy, then that energy is giving you somehow like this. This is your energy, and your particle is moving from one side to another, from a minus x1 to plus. So let's call it x0. Minus x0 to plus x0, because simply it's reflection invariant. If you change x to minus x, it's the same function. So if I have x0, I must have minus x0 as a solution. As a solution of the equation, E equals K equals U, right? U of x. So those are my stopping points, and the particle will move from here to here and then back. Right? And that's the situation which we considered in the class, and the period of such oscillations. The period of such oscillations given by 2m over 2 square root integral from, in this particular case, from one stopping point to another. So one stopping point is minus x0, the other is x0. Otherwise, if it is not so symmetric, the potential, you need to solve this equation and find two stopping points, right? And then integrate from one stopping point to another. Here it's a bit simpler. And then you have the x divided by E minus U of x, right? So it's K x to the fourth and square. So that's the period of oscillations. And if I put here U of x, then it's period of oscillations on any in any potential. Now, but you were asked how that period depends on energy. Now let's see where is the energy in this expression. The energy here is here, right? That's one energy, total energy of the particle. And but there is also energy hidden in this x, in the position of the stopping point, right? Well, first you can see it differently. You can see it because that stopping point that is a solution of this equation which does have E inside, right? That's one thing. And the other thing is sort of absolutely clear from this picture. If I increase energy or decrease it, for example, here, then my stopping point is moving, right, to the new position. So the position of stopping points depends on E. And there is one more E here, right? Now, after that, some of you try to sort of guess the answer at this point. That if I, for example, decrease E here, then 1 over square root of E is increasing, and x0 is decreasing, right? The position of the stopping points are decreasing. So you have something increasing, something decreasing, and then you write. So some of the students wrote that then it means that the period does not depend on it. This is absolutely wrong, right? Because it depends how they increasing and how they decreasing, right? If one process is slower than the other, then they will not compensate each other. And just saying words is not enough. You need to compute it, how exactly it's happening, right? And in this particular case, it's actually not very complicated story. Now, remember that this equation, in this particular case, is exactly that, and all this is where is that whatever is under square root equals to 0, right? Because what is under square root is E minus U of x, right? And that's exactly from this, it means that x0 is a solution of this equation, right? So when whatever is under the integral is 0, under the square root. So let me then do very simple substitution here and say that I introduce variable y, which is equals to x times e divided by k in 1/4. Right? Where it comes from is you will see in a second, because if I do the substitution here, what I have is that t is the period equals 2m over 2 square root. Then I have the integral, and I'll take care of the limits a little later. Then from here, when I have the dx here, right? What I have then is did I write? No, the other way. Sorry. Like that. X equals y times this. So when I now substitute it over here, the x dx, it will be dy times e divided by k in 1/4. Right? Now, when I substitute it over here, I have e here, but now I substitute x to the fourth. I see that I have e divided by k, right? So what will I have is minus e y to the fourth. Right? That make sense?
Yep.
I have a question on how you determine the substitution that you made.
Just 1 second, right? Okay, I'll talk about it. So you see that here is e and here is e, so I can pull it out. And what I will have here is 1, and here I have 1 divided by square root of e. Right? So you see, I'll talk about it just a second. But now I need still take care of those upper and lower limits. But remember that upper and lower limits are the values where this is 0. So they are the values of y where this is 0. So it's from -1 to 1. Right? Or you can just make this substitution into this equation and solve it for y, and you will see that it will plus minus. It's the same thing. All right. Now, why did I do this substitution? Exactly for this reason. Exactly for the reason that now, let me fix this formula a little bit. So it's integral from -1 to 1. You see that what I have here contains nothing. Right? So that substitution which I did was exactly such as to make this integral just a number. You see that there is nothing else, right? If I take this integral, and Mathematica can do that, if I take this integral, then I will get a number. I can compute it, I don't know, numerically if I want, but it's just a number. Which has nothing, no dependence on anything. It's just a number. Right? So I did the substitution exactly to get this form, to get the number. Now, how did I figure it out? Well, believe it or not, but I've been doing physics for the last 40 years. And so I actually know how to do those things. But there is a hint here. It is what is called uniform function. You see that it's a function kx to the fourth of a very, very simple form. I can rescale x to get anything I want in front of it. And what I want in front of it is just e. And I want to cancel k. So I can rescale this function and just like that. It's just simple rescaling of my variable. If I, for example, had something like that, plus, I don't know, alpha x squared, right? Then it would not be possible. And because there is no way to rescale this function to have an arbitrary something in front and nowhere else. And because it's a very, very simple function. That's all. So, but you should play around with that, and I mean it's not many things which you can do here. You can play around with those things, and then you will find it. So now you see that this is just a number, so all dependencies on everything is contained just here in front of it. So what I see from here that t is of the order of e to minus 1/4, right? So it's proportional to e in 1/4, right? 1/4 here, 1/2 here, 1/2 minus 1/4 is 1/4, and it's downstairs. So that's the answer, right? There is some other dependencies here on mass, on k, on whatever, but I asked only about the dependencies on energy, and this is the answer. Right? So well, you can see from here that if I increase energy, if I increase energy, period actually decreases. Right? So it decreases. So if I increase energy, it starts to move faster and faster, and it's actually it is not compensated by the fact that it's moving longer distance. The velocity increases faster than the distance. So that's the answer. So I want you to understand that how simple this is, right? So it's actually, if you try to start with f equals ma and write that equation for this, like a force, right? The force is the first derivative of it. So what you will have is kx to the cube as force, right? And then you have the equation, which is x double dot, the second derivative of x, will be proportional to x cubed. This is very nonlinear equation with very complicated solution. The solution, I think, is some elliptic functions, if I remember correctly. And out of that elliptic functions, then to get the period is actually quite a work. Quite work out. And but you see that here it's all of it. It turns out that all of those complications just give you some number, which you can compute numerically and then well, not compute, just call it a number. And if you're interested only in energy dependence, that immediately is given, right? So in this sense, that's much easier to that's the easiest way to get that period. That makes sense? That makes sense?
Yep.
Yes.
All right. So the next was the same problem, but here you have x squared. X squared, right? So it's the graph of it is almost the same as this one. It's just a little less flat at the bottom. And in my hand drawing, they will look exactly the same. So I will not even redraw it. So we have exactly the same situation here. But now in the integral, what we have here is a 2. Right? That's the power of 2. And that's it. Everything else is exactly the same. So you see that it's 2 here. So in order to get E out, what I need here is to make the substitution when this is 1/2. Right? So then I square it, and what I will see is E in front and divide it by K. K cancels out and E stays out. So what I will have here is factor of 2, not factor of 2, the power of 2. And by the same reasoning, I have here 1/2. And because that's exactly the same. Right? And when I do that, then I see that there's E in 1/2 here, E in 1/2 here. So they cancel each other, and it means the period is constant. Does not depend on energy for this potential. When this potential acts to the force, it actually does depend on energy, and you can actually compute how it depends on energy, how period depends on energy in completely arbitrary potential. Let's put here letter N, and you can, by exactly the same procedure, you can solve for any N. Right? You can try it. I mean, it's actually fun. It's exactly the same process. So, but in this particular case, what you have is that period does not depend on energy, and this is something which should be expected, right? Because when it is 2 here, what you have is harmonic oscillator, right? In harmonic oscillator, potential energy equals kx squared over 2. Here it's no no, there is no 1 over 2 here, but well, let's like put that 1 over 2 inside K. It's our K. We can do whatever we want. So it's a harmonic oscillator, and the harmonic oscillator is exactly when potential energy is proportional to the displacement square. That's the only thing which is important about the harmonic oscillator, right? Everything else is just a bunch of notation. And but what is important about the harmonic oscillator is that and exactly this property. That is the most important property of the harmonic oscillator. There is a big reason for that. For that exactly in this case, period does not depend on total energy, and the reason is some symmetry which is hidden in harmonic oscillator. I'm not going to talk about it, but it's also the reason that symmetry is the reason why problem of harmonic oscillator can be solved exactly even in quantum mechanics. But in this case, so what's important here? You see that it tells you that period of the harmonic oscillator does not depend on energy. So the period does not depend on initial conditions. Right? Remember that energy is given by initial conditions. So it doesn't matter how hard you kick the harmonic oscillator, it will return exactly at the same time, right? After one period. It doesn't matter how hard you kick it. And this is exactly what allows us to measure time. Right? That's the reason why that harmonic oscillator that springs in your watches or whatever it is, it allows you to actually use that as to measure time. If it were not so, then your period of oscillations would have depended on the initial conditions and how hard you kick it. And then the mechanism of any watch would become enormously complicated. I'm talking about mechanical. It will become enormously complicated because now you have to be very careful how that thing kicking, that spring, that pendulum there, whatever it is, right? And it's only this property of the harmonic oscillator which allows you to not care about it and just kick it somehow. It will do its work, right? In some sense, this is the way we measure time. This is the reason when we actually can measure time at all. All right. Any question? Oh, there was another problem there. And
how do you get the limits?
But it's the same thing.
1 and -1.
Yes, yeah, because you can solve this equation, but you see that when you look at it, right, at this, right, the limits are where this whatever is inside is 0, right? Right?
Yeah.
Yeah.
So when I have 1 minus x squared or y squared, right? Y squared square. Whatever is inside is 0 when y equals plus or minus 1, right? I don't even need to solve this equation, but you can. You can solve this equation, do the same substitution there, you'll get the same answer.
Okay, thanks.
All right. And the last question there was, what happens if that k in both cases is negative? Well, again, you can, and it's amazing how complicated students want to make their life. And some people writing about some imaginary parts, blah blah blah, all this stuff. Come on, it's a simple question. If you have potential like that, right? You see that it's a hill. If you place your point somewhere, it will go downhill and never return. That's all. That's all you needed to write. That in this case, that the particle never returns, so it's not a periodic moment. The question about period doesn't make sense. It's much simpler than what you think. What do you think? For some reason, students think that we want to complicate things. In fact, we only want to make them simpler. The simpler, the better. All right. Any questions about homework? All right. So deadline for the next homework is not Wednesday but Friday, and I think I will move everything to that kind of thing. So you'll give me everything on Friday, and I'll give the explanation on Monday, because of that unexpected interruption. We have to deal with that. I have nothing against vacations, unexpected vacations, but I would prefer to know that a little bit more in advance than a couple of hours. All right. Any questions so far? All right. Then let me move on. And I'm not sure I have enough time for that, but to finish. But anyway, so what I'm going to talk about today is another reformulation of mechanics. Remember that last lecture, we were talking about the Hamiltonian reformulation. So it turns out that Hamiltonian reformulation is much easier. Is the only thing which you can extend to, say, quantum mechanics, because forces do not make sense in quantum mechanics. Even the coordinate of the particle doesn't make sense in quantum mechanics. So you have to deal with completely new machinery. But the story is that quantum mechanics should contain classical mechanics as one of the limits, right? Because they must not contradict each other. You must be able to start with quantum mechanics, and in some limit of some large masses, big velocities, and so forth, you must restore Newtonian mechanics. Otherwise, quantum mechanics is not valid, because we are absolutely sure that Newtonian mechanics is working. The same thing with relativistic physics. If we write something else, say that in large speeds everything is different, then when speeds, the velocities become smaller, we must restore Newtonian mechanics, because we are absolutely sure that Newtonian mechanics is working quite well. And it turns out that the only way to do that is through Hamiltonian formulation, not forces, because it's impossible to introduce forces in quantum mechanics to relativistic physics. But energies are still valid concept there, and so it's much easier to do it with that formulation. But then you go to next level, and there is a quantum field theory, and it turns out that Hamiltonians in quantum field theory is a very difficult object to work with, and then there is another formulation which exists for classical mechanics. It's called Lagrangian formulation, and it also can be used in quantum mechanics, but it's what is called the Feynman path integrals. If you ever heard about it, it's actually extension of Lagrangian formulation to quantum mechanics. And but nevertheless, it's another formulation. It's very, very, very different from Hamiltonian. It's actually quite amazing that they actually give the same answer always. They're absolutely equivalent one to another. But for some problems, it's actually easier to use Hamiltonian. For the other problems, it's easier to use Lagrangian. Which one is easier to use is pretty much clear when after you solve a couple of hundred problems on both. And by the way, for classical mechanics, Lagrangian is actually easier, majority of the cases, but than Hamiltonian formulation. But nevertheless, they both play a very, very important role in our understanding how to describe this work. So now and that's what I'm going to talk about today, is Lagrangian formulation. Now I have only less than an hour to do that, and as I said, it usually takes quite considerable time in a specialized class in mechanics to describe it. So I'm not going again. I don't expect you to become experts on it. Moreover, what I'm going to present is some calculations which are actually not trivial. I mean, they are very, very simple, but non-trivial in the sense that they are unusual. And it takes some time to actually get comfortable with those kinds of calculations. So I do not expect you to actually even to be able to repeat what I've done, what I will be doing here. But if you can, please do, because it's fun. It really is. And at some point you understand that it's a very, very, very simple story. There is nothing. But what I'm aiming at is that you at least know that such formulation exists and what it means, and maybe not know how to deal with that, but at least know that it is out there, because it plays quite considerable role in our understanding of modern physics. Okay, so what? In order to do that, I need to introduce some new mathematics. And it may be very much new mathematics, but it's extremely useful piece of mathematics, which is not only for mechanics. For a lot of things, it's actually the only way to approach any problem. And that piece of mathematics starts with the idea of functional. What is a functional? So the functional is a way to, is some sort of extension of the idea of function, right? So I'll start with the function. What is a function? The function is the following thing. You have a set of some objects, right? Let's call A object, and you have some set of objects which we call set B, right? And a function is a map from a set from set A to set B, right? So for any element of this set, you can put the corresponding element of set B, like this. Right? It's a map, right? So for this element, you have another element of set B. For this element, you have another, all the same element of set B, and so forth. So such a map is called a function, right? So the only requirement which we have is what we can call this is a set of elements, right? And this set we will call image. That for example, this element of this set is the image of this element of the set. That's what this arrow means. So any element of set A has only one image. That's the only requirement. So, for example, that cannot happen. Right? That will not be a function because this element has two images. That's prohibited. That we don't consider. Well, not with normal function. But otherwise, that's the definition of function. Now, the definition of function which we used to is exactly the same thing. But now that elements are the same. That elements A and B are the same. One of them is element X, right? The other is Y. Those two sets are the same. They don't have to be different. Only two of them, right? So you have elements of numbers here, set of numbers on which you call X, set of numbers which you call Y, and this function gives you exactly the map, right? So you take one element from set X, and you have a rule to find the corresponding element on set Y. That makes sense?
Yeah.
Yeah.
So that's exactly what it is. That set of rules which give you this map is called a function. That's all. There's nothing else, right? So in particular, I can actually call a function, or it will be a function if I just say that element 1 corresponds to element 3, here element 2 corresponds to element 15 here, and so forth. I just list them all, right? And that list will be called a function. The way we write the functions typically are through algebraic expressions or whatever we use, or some integrals, but whatever you use it. It's just one way of writing the function. You can also write the function just like labeling, just like making a table. But then you will not be able to do that when you have infinite number of elements in both sets, or at least one set, right? It will be difficult to write infinite long. Well, sometimes it's strictly impossible. So, but nevertheless, that's the definition of function, right? So now let me contrast. Let me say what is the definition of functional. A definition of functional is the following: that I have a functional, and its argument is a function. and it returns back a number. I don't know. For each function, so it's the same kind of map, but now this set of elements is a set of functions, and this set of elements is a set of numbers. So for each function, I have a number. Okay, that makes sense.
Yeah.
So let me give you examples.
Yes.
That's actually easier to understand. Let me say that for any function f of x, right, I give you a value of this function at x equals 2, for example, or 3, or 5, or whatever. Right? It will be different functions. This is a functional, right? Because it takes a function and it returns a number. Right? And for each function, there is only one number. Perfect. That's a functional. That functional actually very important. Not with these two, but it's called delta function, Dirac delta function. In physics, we will see those later on. But that's one of the functions. It's completely fine, no problem. Right? So again, if let's just imagine yourself to be a functional. Can you imagine yourself to be a functional? Some specific functional, right? It has to be specified something. A functional is a set of rules, right? Those rules are such that if I give you a function, you return me back a number. Then you are a functional. That set of rules which you have is the function. Okay? That makes
Yes.
sense?
Yeah, that makes sense.
Again, please don't overcomplicate things. They're exactly what I say. Nothing more complicated than that. So let me give you another example of functional. It's let me say that I have a function f of x, right? And it returns that functional returns me, say, integral from some specific number to another specific number of f of x dx. So those numbers are some specific numbers which are given and just nailed down to the blackboard. And so now what it means that if I give you a function, you then take this integral, and this integral will be a number, right?
Yeah.
Yes.
And you return this number back to me. So I give you a function, you return back number. Congratulations, you are a function. Okay?
So a definite integral is a functional.
Yes, of course. If you can consider it as a functional, right? It's a function. So whatever functions you stick in, it will give you a number. And remember that you can always take it. Well, I mean, not always. The functions must satisfy some integrability conditions, blah, blah, blah. Forget about them. For any normal functions, it will be some number, right? And you can always compute it numerically if you want. It doesn't really matter how you compute it, right? So you just stick it in there and then compute this number and return it back. So that's it. That's a function. So yes, definite integral in this case is of course a function. Okay, let me give you another functional and example, and which has actually meaning, right? By the way, that functional also has a meaning, right? It's the area under the curve. So you don't even need to take the integral. You just need to measure the area under the curve. That's all. But now let me imagine the following situation: that I have my x and y, and I have 2 points, xa, ya, and xb and yb. Right? Those points are given to me. Right? Now I draw a path from one point to another. Right? So arbitrary path which is given by some function. Right? It's a graph of some function. that function must satisfy boundary conditions. So y of xa must be equal ya, right? Because that's where I start from. And y of xb must be equal yb. Right? So any function which satisfies these conditions and which is continuous and so forth will provide me with some path from point A to point B. That makes sense so far? So I can consider functionals then, which I will call L of y of x, which is just the length of this path. So it's integral from xa to xb, and then we already figure out what this is. It's y prime squared square root d. Remember that? Come on, remember that?
Oh, yes.
Yeah.
Do you remember that? All right. So what it means again? If I give you some path, right, which satisfies those boundary conditions, coming from here to here, you take that path which is given by this function, you stick it in here. You see what it tells you to do. It tells you to take this function, right, differentiate it with respect to x, right, square it plus 1, take the square root, integrate over the x from given limits, right? What you will get is a number. That number is the length. It's called the length of this path, right? So it's a functional which provides you the length of this path. See, that actually has a meaning, right? Does that make sense?
Yeah.
Yeah.
All right. So you see that we already have two examples of functionals which sort of given by integrals, right? But the first one which I gave you, just area under the curve, right? It's also very good functional. Depends on the function itself, y of x, and this one depends on the derivative of y of x, right? You see this?
Yes.
So the previous one was area of y of x equals the integral again from xa to xb y of x dx. Right? That was the previous example. So both of them, you see that both of them are functionals which depend on the function, right? You need to take the function. So somebody gives you a function. You need to do something with it. Exactly what is prescribed by this equations, by this expressions, and return back a number. So both of them are functions. So let me then do the following thing, and let me consider now a functional of the more general function. So I say that the functional which I want to consider, which acts on some functions, equals integral from xa to xb, and then I have function L, which depends on two arguments. One of them is y prime of x, and the other is keep switching notation, f of x and f of x dx. Right. So it's a more general way to write both of those functionals. Okay. That make sense?
Yeah.
Yes.
So again, let me. I'm sure that there will be a lot of confusion here. It was for me for a while. So this is L, right? L is a function, normal function of two arguments, right? That function and xa and xb define my functional. So if I know that function of two arguments, normal function of two arguments, and those two limiting cases, that's it. My functional is defined. After that, if I give you a function, y of f of x, what you do, you take the derivative of it, right? And you stick it as the first argument of this function. Then you take the function itself and stick it as the second argument of this function. Right? So that now what you will have here after that, remember that f is somebody gave it to you, like me, for example, right? So you know this function, and you know function f. So what you will have after the procedure, substituting instead of first argument the derivative and the second argument the function itself, what you will have is the function of x. Right?
Yeah.
So you can take this integral and it will give you a number. And so this is functional. Okay? So let me see, let me explain it on those examples. So what I need is a function of two arguments. Let's call them psi and chi. Whatever you call it, doesn't really matter. So this particular functional, tells me that my L, so this one, L depends only on first argument. There is only y prime, and there is no y. Remember, those considered completely independent variables now. F prime and F completely independent variables. I just call them F prime and F. Right? So I see that there is only derivative here. So for this particular case, that function L is of psi equals 1 plus psi prime square, psi squared. Right? And there is no dependence on the other argument. So let me just write it like that. I can put nothing here to remind you that there is no dependence on the second argument. Right? So now, if I give you this, you know what to do. If I give you a function, you take a derivative of this function and stick it instead of psi. And then what you get is this, right?
Yeah.
Then you take what you get, plug it into this integral, take the integral, give me a number. And so this is this case. And this case is actually even simpler because now that function L does not depend on derivatives. There's only y here. Right? So it depends only on the second argument. And it equals the argument itself. Very simple function, right? So now again, if you know this function, I give you function y of x, you take it, you stick it in instead of the second argument, you got chi. Chi is the second argument. Now you stick instead of chi, you stick y of x, so it's y of x. You plug it in here, you have y of x dx. Exactly what's written. That makes sense?
And
Yes.
both psi and chi would be dependent on the same variable, though.
No, they are completely independent variables.
So I know they're independent, but I'm saying, like, since, like, for example, we looked at f prime of x and f of x, they both depend on x, though. They both have some shared variable, but they're not dependent on each other. I know
That's
that.
how you look at them, right? Look, it's a very, very different story. You're skipping one step. L of psi and chi is some function. Psi and chi are completely independent variables. That's it. That's the definition. Right? That clear?
Yeah, I'm clear about them
Now,
both being two
Now,
independent
just listen.
variables.
Don't skip one step. Now, there is one step more. If you're given some function, right? If you're given some function, then you can take the derivative of the function, stick it in place of the first argument. Just substitute it instead of the first argument.
Yeah.
Take the function, you substitute it in second argument. Only if you already have this function. In the definition of the functional, This is arbitrary function. This is some function of two independent variables. But in order to use this functional, right, you need to be given a function. You need to substitute derivative here, some function here. Then you can take the integral. Okay, that's a very important distinction for what I'm going to do next. Because now you see that it depends on what I'm doing, how I want to look at it. I want to look at it, if I want to look at it as a function of independent variables, well, that's what I should do. But if I want to compute the value of this functional on this function, on some function, that some function must be given to me. And then I treat that independent variables as one of f prime and the other is f. Okay? So make it simpler, right? It's step by step. All the time. Mathematics is always like that. Don't skip. That's actually the difficult part. All right.
What does the S square brackets mean?
Yeah, that's the difficult. Well, somehow I want to, to denote it. That's a notation. So that's square brackets. There are plenty of ways. There are plenty of different notations. Physicists usually use that square brackets. S with square brackets means functional. So it takes a function as an argument.
Okay.
The function itself has these brackets, round ones, right? And in order to distinguish it, we use square brackets, but not always. And people just write that it's functional, and you need to understand what they mean. But I will try to be consistent and write it like that. Okay.
Okay.
It's just notation for this process. All right. So this is functional, and again, you see that that form of the functional can be describes all the examples which I gave, but you can consider actually more general. You can consider the function of three arguments, and instead of third argument, plug, say, second derivative of f. Right? The same thing, the same procedure. Doesn't really matter. But it turns out that in physics, in mechanics, this is the most important case when this is only function of two arguments, only the first derivatives will appear. Okay? Does that make sense?
Yeah.
All right. Now let me say what do we need for it for? Well, you could have guessed it from this, for example, from this functional. We can ask the following question. This so far it was just the definition of functional. There is no, I didn't do any calculations or any statements. But now, in order to make a statement, we need to figure out what question we want to answer. And the question which we can answer here is the following: which function gives me the minimum of this function? Right? That makes sense?
Yes.
So I have a functional. I can put it some different functions inside. Those functions will give me numbers back, right? I will plot all those numbers and see which one that at some point I will see that there is a minimum, the smallest number which I get, right? Mm-hmm. And I can ask which function gave me that smallest number.
Can you take the derivative of a functional? Is that a thing?
Yes. It's not called derivative though. Yes. It's about how we're going to proceed. That's what I'm going to describe how it's done. So the question is again, I want to find which function gives me the minimum of a given functional. So I have a functional and I want to know which f of x gives me the minimum value. Does that make sense?
Yeah.
Yeah. Mm-hmm.
All right, good. So let's. It's sort of. I don't know if you can understand how it can be done here, but let me remind you about some very simple things about normal functions. So let's imagine that we have a normal function, right? And here is x, here is y. And we can clearly see that there is a minimum here, right? So what does that mean? That's the minimum. Can you tell me, like, let's imagine that I've never seen any graphs. I'm blind, right, for example, or I don't know, I'm out of this world alien, or whatever. And you want me to describe to me what is the minimum? How would you describe it?
The lowest y value of the set.
What does it mean, the lowest?
The smallest numerical value.
What do I need to do to find the smallest? Means that there is some procedure.
Well, it's finding the derivative, but in terms of explaining that to someone who doesn't know it,
Right. Okay.
If you spanned a set of numbers, like if you just like went from left to right or something like that and looked at the pattern, whichever one would be like your lowest value numerically
Right.
speaking.
That's very good. That's exactly what it is, right? You check all these numbers and you find which one is the smallest. That's what you were talking about. Which one's giving me the smallest image? That's correct, of course, but it's sort of it's difficult in terms of this functional. What it means is that I need to put all possible functions in, right, and find the minimum. That's of course correct, but it's absolutely not doable. That's not practical thing to do, right? There are way too many functions, and we cannot plot that same. There is no space of functions which we can plot, right? It's an infinitely dimensional space. So it's very difficult to do in practice. So is there any other properties of the minimum which you can figure out to find out what to describe what minimum?
Ask it one more time.
Is there any what other properties of that minimal point which you can use to describe what minimum is? Kind of strange that already you know calculus and all that. That question always puzzles students. Look at this. Let's imagine that this is the minimum, right? Let's shift a little bit from the minimum, either to the left. This is right, or either to the right or to the left, just by a little bit. What will happen to the value of the function?
y increases.
Exactly. In both ways, it increases, right? It increases, doesn't matter where I go, to the left, to the right, or to the left. Right?
Yeah.
So when I am at the minimum, no matter where I go, the value of the function will always increase. This is a very, very specific property of this point, because if you take any other point here, right, if you go to the left, the value of the function decreases. If you go to the right, the value of the function increases. Right?
Mm-hmm.
But here, this is the only point, well, if the minimum or maximum, well, minimum, right? It's the only point where no matter what side you shift by a little bit, your value of the function will be increasing.
So how would the person that we're explaining this to that's never seen these things before, like without it taking, being too time consuming, and if there was multiple minima, like how would they be able to simply isolate?
Look, let's remember that what we want to do is to find the minimum of this functional, not to explain anything later. This was just an example, because otherwise you will tell me, oh, well, look at this and it's minimum, right? That's
Well,
that's
clarify, you mean like absolute minima for that functional, right?
It doesn't
Not like
really matter. No, absolute minima is always found by simply comparing the value at local minimum.
yes.
Okay. So if you now can find local minima, and it happens to be a finite number of them, we can always just compare them and find the global. But it really doesn't matter in this. It's extremely complicated question. It matters a lot, but not for what we are doing. All right. There are huge research on how to do it more effectively, and that leads you to a lot of NP solve problems and NP hard problems and so forth. there are plenty of research on that. Let's just so, but we want to make simpler. Let's find the procedure to find the local minimum. Okay, and that's of course the local minimum. That property it's specifically designed. You see that definition which I gave you, that no matter where you go, the function increases. It's specifically local definition, right? It cannot know about global property. It only knows about some small neighborhood, and that's exactly what the power definition. Now let's nevertheless see what it means in a simpler case. So let's take any value, any point, right? So say x naught, and let's take the f of x naught, or y of x naught, and now let's shift it a little bit. So let's take x naught and add the delta x to it, a small value. Then what we know, right? What we can, because of functions are sort of smooth and so forth. Plus there is a theorem about it. We know that it will be something like that. It will be delta x times some number a plus delta y delta x squared times b number b and so forth. Right? So close in small neighborhood of any point, we can zoom in and we can see there is some it's almost straight line, but just bends a little bit, and we can write some sort of polynomial in order to approximate that function better and better and better. Of course, you know what it is. It's called Taylor expansion, but I don't want to use those words because there is no Taylor. We don't know Taylor expansion for the function. So I want to do it more generally, and just say that, well, in some neighborhood of any point, we can always write a polynomial with respect to displacement from that point, which will approximate our function as well as we want. Does that make sense?
Yes.
Now let's imagine that delta x is very, very small. Right, this is delta x squared. Delta x squared is smaller than delta x, if delta x is very small. And all the other terms will be a lot smaller than the first one. Right? So what we see here, then if we only keep then the largest term, this one, right? Then what we will see is that delta y, right, the shift of the value, equals delta x times some a. Right? It's just shift of delta y is just this minus this. So how much the shift, the change of the value of the function, right? And the rest of them are much, much smaller. But then what we see here, that the sign of delta y depends on the sign of delta x. Right? Does it make sense?
Yeah.
Yeah.
Imagine that a is positive, right? Then delta x is positive, delta y is positive. Delta x is negative, delta y is negative. But the minimum is exactly such a point where that must not be possible. No matter what sign of delta x, in the minimum, the value of the function must increase. Right? And when a is positive, the value of the function will decrease if delta x is negative. Or when a is negative, then the value of the function will decrease when delta x is positive. Right?
Correct.
So a minimum is such a function when this approximation does not have this term. Linear term, right? So a minimum, and the value of this a, b will depend on which point we take as our x naught, right? So the minimum the minimum is such a function where a at that point must be equal to 0. And that's exactly why because that we know that the number a for functions, number a is nothing but y prime at x equals x naught, right? And that's exactly the reason why the minimum derivative must be equal to 0. That make sense?
Yeah.
So that's the reasoning for all of that. I just want to remind you something which you already know, but emphasizing a much simpler action, in fact. So, in that expansion, the linear term must disappear, right? Then it is a minimum. So that's exactly what we're going to use here. So remember that linear term must disappear. So let's do exactly the same thing for a function. So let's imagine how we started. Let's imagine that we found that minimum. That function which provides us with the minimum of a function. Does that make sense? We imagine that. We assume that we already know. What does that mean that it's minimum? It means that if I take the delta, that function, and I add a little small function to it. So let's say that I found that function and I add delta f here, so that it's now this one. Very nearby. And I don't care how to define the measure. That make sense?
Yes.
Now, here is a trick though. You see that both f naught of x and f naught plus delta f naught plus delta f of x must go from A to B, right? That's my boundary condition. So it means that if the delta f of xa must be equal 0 and delta f of xb must be equal 0, right? Because this one is already has correct value. That makes sense?
Correct.
Right? So you see that I consider only functions which go from A to B. Right? And so I found the function is provided a minimum to me. So it's that function already goes from A to B. So if I shift it a little bit, that shift must be 0 at A and at B. So I don't shift my boundary. All right, so let me take this and substitute it inside this function L. So I have function, and now I have derivative, right? So it's f naught prime of x plus delta f prime of x. That's my first argument. And the second argument is f naught of x plus delta f of x. Right? That makes sense? I just did exactly what I'm supposed to do. I took this function and substituted it in here, in this L. Okay? That makes sense?
Yes.
Okay. Now, but remember that I get that L. This is its first argument. This is its second argument, and L is given me as a function of two independent variables. So let me treat it right now. Those functions, those arguments, as independent variables. It's a function, my function of two independent variables. So I treat it as function of two independent variables. Then what? Then I use Taylor expansion with respect to this argument. So what I will have? I will have L f naught prime of x, f naught of x, plus. Now I need to take the derivative with respect to the first argument. This is called partial derivative with respect to the argument f naught prime. Right? This is just notation for the first argument here, nothing else. It's not some complicated story. It's just my first argument, I take the derivative with respect to the first argument. That's it, right? And now I need to put this here, delta f prime, plus dl with respect to the second argument. It's not derivative over function. It's derivative over the second argument of function L. That's all. And delta F. Right? That makes sense?
Yeah.
Again, don't overcomplicate things. This is just considering this is first argument, this is second argument. I shift first argument by this. I shift second argument by this. I know from Taylor expansion how the value of the function is. That's all. So this is a derivative of the first argument. This is derivative of the second argument. Nothing else. Now I use it inside this function. So inside this function, it means that I just need to integrate this with respect to dx. So I need to integrate this with respect to dx. This is the shift. So you see that this is the value of my functional on function f naught. Right? This one. Just compare this expression with this one. It's as if I just substitute f naught here. So what I can write then is the following: that S of f naught plus delta f, right, equals S of f naught of x plus integral from xa to xd, and then I write what's here. dl over df naught prime delta f naught prime plus dl over df delta f dx. That makes sense?
Yeah.
So you see that it has some flavor of that Taylor expansion, which we up to linear terms, which we have, right? So when we shift argument of a functional a little bit, we get the value of the functional on the original f naught plus something which is linear with respect to delta f. Right? Okay. Now, typical situation, but the problem here is the following: that now when they are inside the integral, I cannot consider delta f prime and delta f as independent variables anymore. Right? Delta f prime and delta f, it's some function, right? I need to take its derivative substituted here. I need to take delta f substituted here. And so they sort of they come from the same functions. They're not independent. And then I don't know what to do here. So I do the following trick. What is written here? What is written here is d delta f over dx, right? It's the derivative of the function. So now I use partial integration on this term. And I leave this term as it is. So what I will have then is s of f naught of x plus then I leave this term as it is, dl over df. This is, again, derivative with respect to the second argument of function L. And then I have delta f here. Then I have here minus delta f minus. I transfer the derivative over here. And I have delta f d over dx dl over df naught prime. Again, this is just derivative with respect to the second argument. This is the first argument. Okay, dx. Plus And here at this point, you see that when I try to compute those expressions, what I need to do, I need to take this expression at point xb, and then this delta f at point xb, right? But delta f at point xb is 0. So I need to multiply by 0. I don't care what is here, it is 0. The same thing here is xa, because delta f of xa is also 0. So this term is in fact 0 because of that boundary restriction. So what we have here is we can get rid of this term. Now in this term, what I have, something multiplied delta f, something multiplied delta f. Right? So let me take delta f out. Write it like this. Minus d over dt delta dl over df not prime. Then I have delta f dx. Okay? Does that make sense?
Is that a ddf or ddt
D,
inside the integral?
dl over df.
Yeah, minus.
Dx, sorry, dx. Dx. It's a differentiation with respect to x.
Good.
Right, so I'm sorry. Getting too long. Okay, well, it's one more step, and only. Now, one more step is the following. Remember that no matter what this delta f is, right? The value of the functional must increase. Does that make sense?
Yes.
It's a minimum, right? That doesn't matter how I shift my function, right? That shifted function must give me larger value because f naught was a minimum, right?
Yeah.
Okay. Now think about it. If let's imagine that for some delta f, this value is indeed increases, right? But then what I can do, I can take another delta f2, right? Which equals to minus delta f previous, right? Then this minus will come in front. And if for delta f, the value of the functional increase, then for delta f2, for different delta f, that value of the functional will decrease. Right? Does that make sense?
Yes.
But that's impossible because f naught is our minimum. So the only possibility then is that this integral equals 0. Then doesn't matter if it's plus or minus. But it must be equal 0 for any function delta f. Because as soon as it's not 0, I take delta f minus delta f. They're both non-zero. One of them will be positive, the other is negative. Right? Does that make sense?
Yeah.
So the value of this integral between xa and xb, the value of this integral must be 0 for any delta f. How is it possible to get? Come on, tell me. What should we do in order to ensure that the value of this integral is always 0?
Multiply by 0.
Set the inside equal to 0?
Exactly.
Yeah.
Exactly. So the only possibility to get that, well, it's actually a big theorem, which quite a few pages of proof, but it's sort of obvious, right? That the only possibility which we have is that what's inside here is brackets is 0. So what we have is d over dx, df over d f naught prime, right? That means dl, sorry. This is derivative of the function L with respect to the first argument, nothing else. Right? Equals dl over df. Right? So our f naught must be such function which satisfies this differential equation. Right? So the finding of the minimum of the functional actually means that what we need to do is to solve a differential equation. This differential equation is very famous. It's called Euler Lagrange equation for functional, and that's it. That solves the problem which we set up to do. That's how we need to find the value of the function which provides us with the minimum of this function. Right? So it's also supplied with the boundary conditions, those ones. So, right, those are the boundary conditions for the functions which we're looking for. Let me show how this Euler Lagrange equation works. That's the last thing which I have to do that, right? Works, for example, for the length of a path. So let's take, this is our functional, right? And our L is this one. Right? So let me, in order to simplify the notation, just say that L equals square root of 1 plus y prime squared of x. Right? And I remember that's already y prime, right? So it's it tells me that it's first argument of function L. So what Euler Lagrange means here is d over dx dl over dy prime must be equal dl over dy. So I look here, I see that dl over dy prime, right? So it is only here. It's my first argument of my function L. So what I have then for this particular case, this is d over dx. Then I need to take L and differentiate it with respect of y prime, as if it is just a variable. That's what partial derivative means. Right? This is just my variable. So the derivative then is y prime of x square root of 1 plus y prime of x squared. That's this part. Now the right hand side, the L over dy. I look here and I do not see y here at all. There is y prime, which is the first argument of my function L. Right? Y is the second argument of my function L. They are completely independent variables. So y prime and y should be treated at that stage as completely independent variables. So I look here and I see that this function does not have y. It has y prime, but it's a different letter. Right? So it means that the dl over dy equals 0. This is my differential equation for function y of x. Right? Now this differentiation d over dx is a full derivative, so I need to treat y of x as a function y of x. Okay? So all we need to do to find the path which gives me the minimum distance from A to B is to solve the differential equation. That's actually very simple to do, because you see that what it tells me, that the derivative over x of some function of x, what's inside, equals 0, right? So whatever is inside is a constant. So what I have is y prime of x divided by square root of 1 plus y prime of x squared equals constant. Right? Does that make sense? But it is
Yeah.
only possible if y prime of x is constant. That makes sense? You see that if this is constant, one constant divided by another constant equals some constant. Okay. So in fact, this equation is equivalent to the following differential equation: that y prime of x equals constant. Now the solution of this differential equation is y of x equals ax plus b. It's a general solution of differential equation where a and b are arbitrary constants. Right? Does that make sense?
Yes.
Now those arbitrary constants must be found in such a way as to satisfy our boundary condition. Right? So that function actually goes from point A to point B. But those boundaries, I have two boundary conditions, and I have two unknown constants. So I can always find it. I don't want to do that because my point is that this is a straight line. Right? You see this? This is the constant, this is the constant, this is straight line, and those constants are such that my straight line goes from point A to point B. So the path of the shortest distance is a straight line. Our standard Euclidean straight line. That makes sense?
Yes.
So that's a typical problem, and you can think about. I'm sorry. I'm sorry. That typical problems. Like for example, if you want to have if you have a rope, right, fixed on 2 points, and you want to find what is the shape of that rope. And so what you want to do really is to find a shape of the rope which minimizes the potential energy. Potential energy is a number. Shape of the rope is function. So you need to find such a function which minimizes the function of potential energy. So you need to first write it, then write Euler Lagrange equation. You can the form of the soap field, the same thing. It minimizes potential energy. You do it, right? Strategy of investment, right? You invest money. This is that your investment can be sort of function of time, right? You take and give money, and your functional is the finite value of the money you have in your bank account. You take you write the finite value of the bank on the bank account as a functional of what you do, right? And then you find the maximum of the function, and that's your strategy of investment, and so forth. So actually, in fact, majority of the problem which you have are the problem of the kind of find the minimum or maximum of the function. You just haven't thought about it before, so please do it. Think about it. What are those problems in terms of function? All right, any questions? And again, if you get scared about that, please don't, because I'm not going to ask you ever to do any calculation like that. But if you think that it's cool, I think it's enormously cool. In fact, that kind of thing. It's really not that difficult in reality. Again, it's a very simple story, and you can study it on your own. You have a new technique under your belt. All right, any questions? All right, then that's it for today. And I have office hours today, right? And I'll see the rest of you on Wednesday. Yeah, sure. Okay. Yeah. Can you hear me? Look, it's written on Canvas, on the home page of the Canvas. I don't know where the conflict can appear. If you go there, it's written. It's a take-home exam. It's given dates for it and so forth.